Okay, we're going to go over velocity time graphs for A-level maths, and this is something that can actually come up either in an A-level paper or an AS paper. So whatever you're revising for right now, this could be helpful. This question, we have a car setting off from a point A, car traveling along for a bit, and then we say 4 seconds later, a motorbike setting off, starting at constant speed and then beginning to accelerate. And the whole point of the question is, at which point will they meet? Which point will the bike catch up with the car? So first, I guess if you need a quick recap on how these graphs work, let's go to the side over here. We have for a velocity time graph, like so. The important things you need to remember is that the gradient of the line is equal to the acceleration of the object. Okay, that's important. The gradient is the acceleration, and the area beneath the curve or the line and the axis will be the distance travelled or the displacement. Okay, so this is true for velocity time graphs and also for this is true for velocity time graphs and also speed time graphs. Okay, the only difference between a velocity graph and a speed graph would be that the velocity graph could go sort of beneath the axis because velocity can be negative, whereas a speed graph could not go below the axis. It can never be negative. But they both have the same rules of the gradient, acceleration, area, displacement. This question doesn't have a distance time graph, but I guess just in case that you're wondering, if we have a distance time graph here, the rule here is that the gradient is the speed. Okay, there's only really one rule for these. There's nothing. The area, it doesn't represent anything that we sort of use. Okay. This was asking for velocity time graphs, so we'll go over those today. First, we're just asking us to draw the graph. Okay, so let's do one here. Let's have velocity time. Let's start with the car. The car starts at t equals 0, and it travels. Sorry, it also starts from rest. That's important. So from rest, we know the initial velocity of this car will be 0. It travels with a constant acceleration. Okay, constant acceleration. So remember, on a velocity time graph, acceleration was gradient. So constant acceleration means constant gradient, which means straight line. Constant gradient means straight line. And the gradient of that line will be free with gradient acceleration. So we can draw that in. Let's draw it all the way here. So this will be the car, and the gradient of this line will be free. 4 seconds later, a bike sets off from point A. So starting from the same point, where it starts from, it wouldn't actually make a difference on our graph, but we use that later. Travels, in the same straight line of the car. So traveling in a straight line, that's just something they say. It doesn't mean the line has to be straight. It's just like how on a slope you always travel up the line of greatest slope. On one of these one-dimensional problems, you travel in a straight line. Starting off at a constant velocity of 5. So our bike, it's not going to start from the axis down here, because that would have like an initial velocity of 0. See, we know our initial velocity is actually 5 meters per second here, so my line needs to sort of start from a point which is 5 meters per second at time equals, what was that, 4. An important point is, does this line, it goes like this, does it start below this line of the car or does it start above? If this was a question, there would be marks for getting this correct. So you have to think, well, after 4 seconds, I know the velocity of my bike is 5 meters per second. So you're going to have to calculate the velocity of the car. I always say for velocity time graphs to try and avoid SUVAT. You can use it. I think it can lead to mistakes in more complicated questions, and you don't need it. It can all just come from straight lines. So in this example, I know the car, if you think about the equation of this straight line, it's just going to be y equals 3x, because it's a line of gradient free, which goes through the origin. Properly, you should write v equals 3t, but I'm just trying to make things as sort of simple as possible. If the line has equation y equals 3x, then I know when the time is 4, when the x coordinate is 4, I know the height would actually be 12. Right? So that's how I knew to start off my bike beneath this line of the car. Now the bike travels with a constant velocity for 6 seconds, okay? Constant velocity, well the velocity is the y-axis, this just means it's going to be a horizontal line, and it's going to go for 6 seconds, so we'll go until 10. I'm just going to redraw this a bit, because I think I'm going to run out of room for the next bit. It's going to make this a little bit shorter so I have room. Okay, I know it's not quite to scale, but it doesn't really matter. Right, and then the bike will begin to accelerate, constant rate of 5 meters per second squared. So this will now have a gradient of 5, which is steeper than my gradient of 3 of this car. So it's going to be a steeper straight line. Try and get this really nice. Okay. So here, this will be the bike, and the gradient of this line is 5. So I've drawn the velocity time graph. Assuming they both carry on with the same acceleration to the bike catches the car. Yeah, so part B is saying the vehicles will meet at point B, so the bike will catch the car. And basically, where is that point? How far is it from the starting point? So a super common mistake would be saying, oh, this is where they meet, right? This is where, the lines cross, this is where the bike and the car meet. That's not correct. Okay, this point on the graph where the lines meet represents a point in time where the car and the bike have equal velocity, right? They have the same value of velocity on the y-axis. That doesn't mean they're in the same point. That doesn't mean they're in the same position. Okay, they will meet when, they're at the same point, and because they've both started from point A, the bike and the car will meet when they've traveled the same distance. Okay, so at some point in the future, I don't know where this is, so I'll call this just capital T here. I don't know how far in the future, after 10 seconds, but at some point they will have traveled the same distance, which means they will be meeting because they set off from the same point. So how do we represent distance on a velocity time graph? Well, we just mentioned it. Distance is the area underneath the graph. So if I'm solving or I'm trying to find where they meet, I'm going to say same distance, which means they have to have gone the same area. Okay, so, and we can figure that out. Again, I'm not using SUVAT here. SUVAT, you have to kind of break it up into each different straight line section. You have to sort of bear in mind that the bike sets off 4 seconds later. That will affect you. You have to use t and t minus 4 for the value of t in that SUVAT. It's a little bit simpler just to do sort of just equations of straight lines. So let's say the area of let's do the area of the car first. That's easiest. The car, because it's just a straight line, just a triangle with base, it starts off at 0 and it goes up to time t. And the height of this car, well, this is where we use our sort of straight line equation, okay? The equation, let's just zoom out a little bit. The equation of this car, there we go. The equation of this line for the car, we just said was y equals 3x. So at the point where they meet at time t, if the x coordinate is t, the y coordinate will be 3t, because y equals 3x. So the height of this is 3t. So the area is equal to 1/2 or 3/2 t squared. Okay, just the area of a triangle. Let's do the same with the bike. The bike's just a slightly more complicated shape. We do have to split it up. The area or distance of bike. Well, the bike starts off in a straight line for 6 seconds. That's quite easy. 6 down here, and the height was 5. And then the bike, well, it goes in this sort of, it's a trapezium, right? It has this vertical section here, straight line, no vertical section. So what can we fill in this trapezium? Well, let's start with the height of the trapezium, okay? So 10 seconds here, t seconds here. This distance here will be t minus 10. So it's t minus 10 along the base here. This height is nice and easy, it's just 5, it's from before. And same trick we did with the car, to find the final height here of this trapezium, we want the speed, or the final velocity. It's going to be the y-coordinate. So what's the y-coordinate? Well, I'm going to find the equation of the line first. So I want this point here. What's the y-coordinate? I'll go in blue. We'll do the equation of this line. Okay. Well, the gradient of this line is 5. and it passes through this point here. We know the line passes through the point where x is 10 and y is 5. So if you just work out what c should be, if it's y equals 5x plus c and it goes through this point 10, 5, you'll find that c is negative 45. Okay, so y is 5x minus 45, which means the y value here will be 5t minus 45. Okay, so the height of my trapezium is 5t minus 45. I just got it from the equation of a straight line. That's all I did. And now we've done all the hard work, right? We've done all the mechanics. Now it's just down to the sort of pure maths. Can we solve this to have the same area? So 3 over 2t squared will be equal to 30 plus half a plus b h. Okay, area of trapezium. I guess I'll times by 2 both sides. And that becomes 5t minus 40, t minus 10. Let's just bring this up over here. So 3t squared is 60 plus 5t squared minus 90t plus 400. Let's bring it all to one side. 2t squared minus 90t plus 460 equals 0. What were the values of t here? See, 2 minus 19, 460. Okay, so we get 39.1 or 5.9. Now I just look at the velocity time graph over here. The time t at which they meet is clearly greater than 10. It's after 10 seconds. So I can reject my 5.9 solution. I will say they will meet after exactly 39.1 seconds. Not quite what the question asks. It asks how far away is that point. So I'm just going to need the distance traveled. So if I substitute my t into either one of my distance expressions over here, that should give me how far it's been traveled. Let's go in that left expression for the car. It's a little bit simpler. The distance was 3 over 2t squared. So just subbing this in. I get 2,296 meters to the nearest meter. It's not exact, okay. So this is something they can definitely ask in a question of one vehicle catching up another, and you need to set up this equation and make the areas underneath those different lines equal. Hopefully this kind of explains, you could do this with Suvat, but I just think if you just find the equations of all the straight lines in question, you should be fine. So you just make sure to label it like an unknown time t that you're solving for, and then the final y coordinates to find your areas can be written in terms of that t. So because the equation was y equals 3x, or the equation was y equals 5x minus 45, it's very straightforward to find those dimensions on those shapes and to get those areas. So I hope this is helpful, and let me know any other topics for applied for the exam coming up.